Thanks, Paul. Yeah, so yeah, thank you for inviting me to this thing. It's a great pleasure to be speaking here. I'll be speaking about some work from a few years ago now, joint with Matija Bucic and Alexei Pokrovsky and Benny Sudakov on, as Paul said, Rota's basis conjecture. Yeah, the first thing I would like to say is that this work is it turned out it's really completely elementary, and I tried to make the talk so that this, I mean, even if you don't know what a Matroid is, I hope that you will be able to follow. So please interrupt me if I hope that you can interrupt me. I hope that that's a possibility if you don't understand something. Okay, so let me introduce the setting as follows. So I have an n-dimensional vector space V over any field, and I have a sequence of n bases B1 through Bn. So these are n bases, not n vectors. So in total, I have n squared vectors. Every basis in an n-dimensional vector space has n vectors. And then I define a transversal basis to be a basis which contains exactly one vector from each of my identified bases. So that's a definition I can make. And then maybe the most natural question I might want to ask is, does a transversal basis exist? So that's a natural question. Does a transversal basis rather always exist? So this is a very easy question. The answer is yes. And not only does one exist, but I claim that I can construct one in the greedy fashion just by making arbitrary choices, and I'll never get stuck. So let me illustrate that with an example. So here my vector space is R squared, is the plane. I have two bases. The first is a standard basis, and the second is this funny basis, which consists of the vectors 2, 0, and 1, 1. Let's check that there's a transversal basis. So a transversal basis would have a blue element, a vector from B1, and would have a green element, a vector from B2. Let me completely arbitrarily pick the first element of B1. And now if I want it to be a basis, the green element I choose better not be 2, 0, because 2, 0 would be dependent and it wouldn't be a basis. But I can choose 1, 1. Okay, so I have a transversal basis. And maybe you can already see that when I do this, if I add n vectors one at a time, I'll never get stuck. There'll always be some freedom. And the reason is this simple combinatorial fact about vector spaces. So it is a fact that in any vector space, if I have two sets of linearly independent vectors S and T, and if S is bigger than T, then there's always a vector in S which is linearly independent to everything in T. So I would repeatedly apply this. At each step, S would be one of my n bases, and T would be sort of the partial transversal basis that I've constructed so far. And this fact would tell me that at each step there's something I can add to make it work. Okay, so a transversal basis always exists, and maybe a second question is there more than one transversal basis? How many exist? And that is what Rota was. That's the direction Rota was thinking about. Maybe when he made his basis conjecture. So Rota's basis conjecture says that in this setting, there are always you can always find n disjoint transversal bases. Yeah, so n is the most you could possibly hope for, clearly, because there's only n squared vectors. Each basis has n vectors. If you want them to be disjoint, you can't do better than this. So let's just check that it's true in this small example that we had. So I have my first transversal basis B star here, and maybe, I really don't have any choices here. If I want a second transversal basis, it would better use the remaining vectors from B1 and B2. And I can do this. So I can put 0, 1, and 2, 0. That's a basis. It's completely disjoint from the first, and it's a transversal basis. So Rota's basis conjecture is true in this case. But something that is important here is that, well, this fact told us that the first transversal basis we could never fail to find. But that is not true if we want a second transversal basis, and it's possible to make the wrong choices and get stuck. So to illustrate that, let's imagine that instead of choosing 1, 0 at the beginning, we chose 0, 1. It's still a transversal basis, but now we're stuck. Now, if you look at the remaining two vectors, they're 1, 0 and 2, 0, and that does not form a transversal basis. They're linearly dependent. Yeah. So perhaps this is some inkling of what the difficulty is here. The reason this is a hard conjecture is because if you're trying to build these things, you've got like lots of choices and no obvious way to point you towards the right choices, but you do have to make the right choices, because if you make the wrong choices, you get stuck. Yeah, so that's the type of problem that it is. Okay, of course, this is a question about linear algebra, and in linear algebra, I don't just have to construct things in sort of iterative ways, and I can use tools from algebra like determinants. Like if I have a matrix and its determinant is non-zero, that tells me that something is a basis. It tells me that the columns are a basis for the span space. And so you can try to prove this by playing with determinants. And if you are very clever, you can prove this theorem. So this is really summarizing two theorems by Driscoll and by Glynn, which is building on a reduction which was first proved by Rota and Huang and was simplified by On. And it says that Rota's basic conjecture is true in the case where your vector space is over the real numbers and the dimension is an odd prime plus or minus 1. As I said, you prove this in an algebraic fashion, actually not using determinants, using hyperdeterminants, whatever that means. Okay. So that is, so it's not a complete resolution to Rota's conjecture, but it is good progress. Of course, it's got a very different flavor to the combinatorial stuff I was talking about a second ago. And maybe you could object that using algebra for this combinatorial question about rearrangements is somehow cheating. And so you can also conjecture, and Rota did conjecture, that this conjecture is true for, in some sense, non-algebraic reasons. Meaning that, one way that you can make something like that precise, which Rota did, was that it holds not just for vector spaces, but for a combinatorial generalization of vector spaces called matroids. Okay, so now I have a definition of what a matroid is, which perhaps is unnecessary in a matroid seminar, but in case there are people who are not matroid people here, this is what a matroid is. This is one of multiple equivalent definitions of a matroid. A matroid is a system of sets, that is to say a set of sets, M, such that two combinatorial properties hold. The first is that it's closed onto subsets. So if a set S is in my matroid and T is a subset of S, then T is also in my matroid. And the second property is, it's something that closely resembles this fact I had, this fact about vector spaces I had a moment ago, which is that if I have two sets in my matroid, and if one of them's bigger, if S is bigger than T, then there's always some vector, there's always some element in the bigger set, which you can add to the smaller set to get something in the matroid. So this is, I don't think this is standard notation, but this is the notation I'm going to use for adding an element to a set. Okay. So the sets in a matroid are called independent sets, and a maximum dependent set is called a basis. So because we have a notion of a basis, we can equally well formulate Rota's basis conjecture. It makes sense in the general setting of a matroid, and that's the general form of Rota's basis conjecture. Yeah, so hopefully it's clear what's happening here. This is like isolating two combinatorial properties of a vector space and saying let's just impose those and not the rest of the vector space. Okay, so an obvious example of how to get a matroid is to take any vector space and take the collection of all sets of linearly independent vectors in that vector space. Yeah. But this is not. You only get a vanishingly small proportion of all matroids by doing this. Okay, so that is the problem. Let me tell you a little bit about some of the progress that has been made on this conjecture over the years. So the first thing is that well, if it's hard to prove for general n, you can try and prove it for small n. So this is very easy if n equals 2 or 3. It's just more or less checking some cases. If n equals 4, it's, well, it's still a finite check, I suppose, but it's a very complicated one. And there was a computer-assisted proof verifying this, actually in some, I think some undergraduate research project by someone called Chung, who checked this for n equals 4. And that's as high as is known. It's not known for n equals 5. So that's one thing you can try. Another direction, which I like, is that, well, if I can't find n disjoint transversal bases, how many can I find? What kinds of lower bounds can I give? So to my knowledge, there are two things proved in this direction before us. The first was by Gillen and Webb, who managed to show that there are of order square root n many transversal bases in the same setting where I've got n bases of size n. And the second was by Dong and Gillen, in which they proved there are of order n over log n many disjoint transversal bases. Yeah. So actually, I think both of these are quite beautiful proofs. The second one in particular was, I think, what got us interested in this problem. As you may have noticed, none of my co-authors are really Matroid theorists. But this proof was using the probabilistic method, and we're not Matroid theorists, but we all are sort of quite familiar with the probabilistic method. So we thought we could make a contribution to this problem in that way. It turned out that what we did had nothing to do with the probabilistic method, but still, this is a paper worth reading, I think, and perhaps ideas that can be further applied. Okay, so those are some of the things that have been proved. I don't want to get too off topic and describe things that aren't really related to what I'm talking about today, but there's been lots of other work on this problem. It's been quite a popular one. Maybe worth mentioning in particular is that there was this there's this thing called the Polymath Project that was initiated by Terence Tao and some others, where there was this initiative where they tried to bring people together to work together and solve a problem of the internet. And one of the topics they did this on, the 12th one, was on this conjecture, Rota's basis conjecture. And so, yeah, there's a lot of interesting observations and they considered some various twists on the problem, which also raised awareness of the problem, which is good. Okay, so that is something about the history of the problem, and then what we proved. So our result is that in this setting, where you've got n bases in a rank n matroid, you can find at least, well, almost n over 2 disjoint transversal bases. So this improves these two results of Gillen and Webb and Dong and Gillen. Okay. Are there any questions about that before I get into the proof? Okay. Yeah. So so our proof of this is quite simple. I think it's about 10 pages long and completely elementary. So I hope that I can actually maybe outline, but hopefully give you most of the details of how the proof works. Except that there's a few small, it's a simple proof with a few small issues that are annoying to fix, but somehow aren't really conceptually that interesting. So hopefully nobody notices when I ignore them. Okay, so let's, before I get into the proof, let's start with one simple observation is that I would like to, the problem is about you have a matroid or a vector space and you've got n bases in that vector space. I may as well assume the entire matroid consists of only bases. So the matroid has only n squared elements and they are n bases, just because you can delete some stuff and you still have a matroid. Okay, and the second thing is, I don't know if this is a thing Matroid theorists like to do, but it's a thing I like to do, which is I would like to consider these n bases to be colors. I guess I already had a blue basis and a green basis before, but I'd like to do this. So I've got n bases, that's n colors, and so let me define a rainbow independent set in a matroid. In this setting, to be an independent set in the matroid sense, in which every element has a different color. That is, every element comes from a different basis. Yeah. So, I mean, in this language, what I'm looking for is a rainbow independent set of size n. That's what a transversal basis is. Yeah. Yeah. So there's a bunch of interesting questions about rainbow structures and graphs, which I think this can be viewed as a problem of that flavor, and I think it's a helpful way to think about these problems. Right. So a rainbow independent set of size n is a transversal basis. Trivially, the empty set is a rainbow independent set. So the goal for how we will prove this theorem is just to start with empty sets and just keep building them up in some iterative way until we have transversal bases. So recall that we were trying to prove that we have almost n over 2 disjoint transversal bases. So what we're going to do is we're going to consider some collection curly f of little f disjoint rainbow independent sets. Where little f is almost n over 2. We're going to define the volume of the family curly f to be the total number of elements among all the rainbow independent sets in my family. And I'm just going to try and prove this statement. That whenever my family has volume less than Fn, meaning it doesn't yet have F disjoint transversal bases, then I can do some sort of local move. I can move some things around, add something, somehow increase the volume of this family. So clearly, if I can prove this, I can iterate it. So if I can prove this, then by induction, I will have proved my objective. Okay, so that's a super high level of what the strategy is. But just to say a little bit more before I actually start proving things. So we're going to actually accomplish this in 2 steps. So what we're trying to do here is show that I can modify a family curly f to increase its volume. And I'm going to do that in 2 steps. So the first step is the obvious thing, which is, the sort of thing that we saw with the green and the blue basis, that maybe I can just trivially add something to my family of rainbow independent sets. Maybe there is some element which doesn't already appear in my family, such that I can just add it to one of my rainbow independent sets. So because it didn't already exist, it preserves disjointness, and maybe I can just add it to something and maintain the rainbow independent set condition. So this would just be saying that the curly f is not maximal. So I can add something. Something about this notation. I'm going to write notation like this all the time. It's not strictly speaking correct because curly f, it's really a set of sets of Matroid elements, not a set of Matroid elements. But nevertheless, I'll write this. This just means that x does not appear in any of the rainbow independent sets which curly f contains. Okay, so the naive hope is that I can add something to one of my rainbow independent sets and everything will be good. But maybe that's not possible. In general, it's not possible. In which case, I move on to step 2, in which I try to make swaps. So a swap means that I remove something from somewhere in my family and I add something somewhere else. So the net effect is that I've made some local change without changing the volume of the rainbow independent set, without changing the volume of the family. So the idea is that if I remove something, I create freedom to add something else. So there should be ways to do this. And in particular, if step 1 fails, it turns out that there's lots of ways to do these swaps. Lots of ways to make local changes, which give me different outcomes, slightly different outcomes of curly f, which have the same volume. And then for each of these different outcomes, I want to go back to step 1. I want to try again to just add something. Maybe I fail again, but then I just keep iterating through this. So like in terms of what's actually happening here, it's like I'm considering some branching tree of different possible outcomes of curly f, some different possible outcomes of the family, each of which is obtained by like these repeated swaps. So as I go deeper down the tree, I branch out to more and more swaps. And because there's so much freedom to make these swaps, well, I claim, this tree will sort of branch out and get sort of wider, and eventually have so much flexibility that step 1 must be possible. You've freed up so many options. There must be some way to just trivially add something. Okay, so that is the plan. I guess I'll ask again if there are. I don't know if people can actually answer me if I'm asking for questions, but I'll continue to do so. Okay. Yeah. So. Oh yeah, I wanted to say that I mean this kind of idea is is by no means new to us, at least this sort of general strategy. Maybe the most famous kind of method that is like this is augmenting paths to find matchings in graphs. But maybe something a little bit closer is the idea of Porsche rotations to find Hamiltonian cycles in graphs. This kind of idea that you want to do some operation which increases flexibility, and you want to iterate that in order to allow yourself to add something, to increase something. Very good. So now let's start to actually prove some things and prove that this procedure works. Okay, so I would first like to define, I will say an element is directly addable, an element X is directly addable to a rainbow independent set S, if S plus X is a rainbow independent set, which this really means two things. It means that X is independent in the Matroid sense to S, and moreover, it means that X is different color to everything in S. So step one in this outline was really about direct addability. This was really saying that there is something outside the family which is directly addable to something, to one of the rainbow independent sets in the family. Yeah, so this, so the simplest thing we can do is directly add something. As a warm-up, let's prove this fact. I'll call this fact 0. That there are many ways to directly add something if you have a family, if you have a rainbow independent set, which is not very large. So if you have a rainbow independent size, well, for any rainbow independent set, there are at least n minus the size of S many elements that are directly addable to it. So this is a super trivial fact, which maybe I don't even need to give a proof for, but here is one. So you just think that there are two things that make something directly addable. It needs to be in a different color and it needs to be independent. So the number of colors that don't appear is n minus S. And for each color which doesn't appear, there are n minus S things in the size n basis which are independent from it. So this kind of reasoning, if you're not used to thinking about matroids, maybe think about vector spaces and sets of linearly independent vectors. Hopefully this is clear. Yeah, so so if you have some notion of being able to add something, and you have some lower bound on the number of ways, on the number of choices you have, then this is going to tell you something in the setting of Rota's basis conjecture. So here is a very simple and nearly trivial corollary of this fact 0. That in the setting I have n bases in a rank n matroid, I can find at least n over 4 disjoint rainbow independent sets of size n over 4. The reason is just I apply this counting lemma. So, I mean, if I had if my family curly f, if I had some n over 4 disjoint rainbow independent sets, and there was one which didn't yet have size n over 4, then I could just apply this lemma. This would tell me there are many things which are directly addable, but the volume of the family is just not that big. It's bounded by n times f, and so there must be something that's directly addable which isn't already in the family. So this is really just an illustration of the kind of strategies that we will use to prove things. This is a completely wasteful proof, and moreover, there's simpler ways to prove this fact. But that is a corollary of fact 0. The fact 0 is about directly adding things. So now let's think about what you can do if you swap something and then add something. So what extra freedom does a swap give us? So here's a slightly more sophisticated definition. I'm going to say that an element X is one addable to a rainbow independent set S if there is X primed in S and Y not in the family, such that S minus X prime plus Y plus X is a rainbow independent set. Okay. So I want you to think of this as being really the concatenation of two operations. The first one is a swap. So I'm swapping X prime with Y. And here I'm imposing that Y is not in the family, so this swap on its own does not create any conflicts. So things are still nice and disjoint, and we're happy after the swap. And then hopefully the swap will have given us some freedom to add something, so then we add X. Okay. That's what being one addable means. And as for the colors here, it's not really part of the definition, but in practice, X prime and X are going to have the same color, and the idea is that I'm removing something of the green color here, which allows me to add something else of the green color. So I'll color various elements for the rest of this talk, and really that just means I'm keeping track of this sort of thing. Okay, so that is what a one-addible element is, and let's count one-addible elements. Let's have a more sophisticated version of fact 0, which says that there are always at least n minus s times n minus f elements which are one-addable to a rainbow independent set S. So of course, what we had before was n minus s squared. So if S is close to a transversal basis, if the size of S is close to n, this is a much better bound, which we get from the flexibility that a swap gives us. So this fact is, again, nearly trivial, but we'll have a proof. So, okay. So here's the proof. So first I'm going to fix a color B, which does not appear on my rainbow independent set S. And we can assume there is such a color B, because if there's not, the bound is 0, and that's trivially true. So we first claim that we're going to break up the one-addability thing into the two parts, the swap and the add. I first claim there are many ways to do the swap. There are at least n minus f elements x primed, which can be swapped for a B colored element in the sense that there is some y of color B not already in the family, such that s minus x prime plus y is a rainbow independent set. So why is this? Well, let me do this. Okay, so the reason this is true is as follows. If I let S prime be the set of all x primed which can be swapped out in this way, so all x prime for which there is some y for which this is a rainbow independent set, and I suppose for contradiction there's not enough of them. This set has size less than n minus f. Well, the curly f itself only has at most f elements of color B, because each of its rainbow independent sets is rainbow. So the family has at most f B colored elements, but in total there's n. So because S prime has size less than n minus f, one of these B colored elements which does not appear in the family must be independent to S prime. Okay, so I get a rainbow independent set, and then I use the Matroid property. The Matroid property says that if I have two independent sets of different sizes, I can sort of add elements from the bigger one to the smaller one, and I can repeat this until they have the same size. So I'm going to do this. So in order to get S primed, I've deleted some stuff. So I'm just going to add back some more stuff from S until I have the same size as I started with. I can do this by the Matroid property. So I add back all these elements, and so I'm going to get all of S except one element, because I've added y, so I'm going to be one short. It's going to be all of S except one element x prime primed plus y. And by construction, x prime primed is not going to be an S primed. It's going to be one of the ones that I deleted to go from S prime, to go from S to S prime, to go from S to X prime. But of course, this is a contradiction, because what I've done here is I've swapped x prime prime for a B colored element. And well, we're assuming that, I mean, S prime was a set of all elements which can be swapped. So that is a contradiction. So what we have just proved is that there are at least n minus f elements which can be swapped for a B colored element. There are n minus f ways to do this operation. And now the rest of the proof looks basically the same as for direct addability. For each of these colors that we know how to get rid of, there are at least n minus s ways to put an element of that color back in. So yeah, here's the end of the proof. Yeah, so for each of the n minus f colors that we know how to get rid of, that we know how to swap out from S, we can look at the basis of all colors, of all elements in that color, and there are at least n minus s of them that we can put back in. And so that's going to give you n minus f times n minus s ways to do a swap, then add something. And you can check that all of these are really distinct, because, well, each of the elements x prime that you know how to remove are of a different color, which means all the elements that you add are going to be of a different color. So this is, I'm not cheating you here. Okay, so we now have a lower bound on the number of one-addable elements. And in just the same way that I can prove some simple fact in Rota's basis conjecture using counting for directly addable elements, I can do something similar here. This fact is still trivial, and this is still not really a good way to prove this fact. but at least this is something that we couldn't prove with fact 0. So this is a corollary that I can find root n many disjoint rainbow independent sets, each of which is almost a transversal basis of size n minus 2 root n. Okay, so still haven't managed to prove anything that's non-trivial, but let's go even deeper. And instead of doing a swap then adding something, we're going to do 2 swaps then add something, and hopefully this will help. So here is a long and complicated definition, but I'm going to explain it to you, of when an element is 2-addable, which is really just iterating one addability twice. So here, let me read the definition to you. I'm going to say that an element x in my Matroid is 2-addable for a rainbow independent set S1 in my family, if there is a second rainbow independent set S0, and a whole bunch of elements in various sets, such that these 2 things hold. These 2 things need to be rainbow independent sets. So this first thing is saying that some element x0 is 1-addable to S0. So I can do a swap. I can swap x0 primed with y0, and y is not in the family, so this won't create conflicts. Then after doing the swap, I can add x0. So this is 1-addability. And so before, if there had been a 1-addable element which does not already exist in the family, that's exactly the kind of thing we were thinking about before. But maybe that's just not possible. Maybe x0 does appear somewhere else in the family, so I'm not allowed to add it. But then I can just sort of push something around and keep going. So I know how to add x0, which means I get to remove it from somewhere else. So wherever x0 was before, so x0 was in S1, I remove x0 from S, and now I have a smaller rainbow independent set in which I hopefully have more freedom to add stuff. So I take, so the second condition is saying that the element x, which is supposed to be 2-addable, is 1-addable to this modified rainbow independent set S1 minus x0. So meaning I do a swap, I swap x prime with y, where y is not in the family, and then I add something. Okay. So this definition has the same property as direct addability and 1-addability, which is that if you're able to find an element which is 2-addable and does not already exist in the family, then you're happy. Then you can somehow do a sequence of moves and increase the size of your family. So the sequence of moves here would be you swap something, you move x0 from S1 to S0, you do swap something else, and then you add x. And the net effect of that is that you increase the volume by 1. Okay. Oh, and another thing I should mention is that, well, I guess you want these elements not to collide with each other. So you want them all to be disjoint and various things. It's kind of annoying to deal with that, but it's something I'm going to ignore, which is not terribly important. Okay, so maybe I'll leave that on the screen for a second, but that's what it means for an element to be 2-addable. And now I'm going to do exactly the same thing as before. I'm going to prove a lower bound in the number of 2-addable elements, and hopefully that will be good for me. So here is a lower bound. Unfortunately, it looks a little bit more complicated. It's got a case in it now. So what it says is that if I fix a rainbow independent set S0 in my family, and I suppose that there are no elements X which do not already exist in my family, which are 1-addable for S0. So I'm allowed to assume this, because if this didn't hold, if there was something outside my family that was 1-addable, I could just 1-add it. I'd be happy. But I need to assume this doesn't hold in order for the next thing to be true. So if that doesn't happen, if all the elements which are 1-addable for S0 fall back into the family, then I claim I have this lower bound. Then there is some rainbow independent set S1 somewhere in the family, which has this many elements which are 2-addable for S1. So the expression we had before was n minus s squared, and this differs from that by a factor of n minus f over f. Right? So that factor is going to be bigger than 1 if f is less than n over 2. So that's perhaps the main reason, well, really the main reason why we're only able to get halfway, because we're going to end up iterating this, and we want things to blow up to infinity. Yeah, so this is a better bound than the previous one if f is less than n over 2. Okay, So again, this is not a difficult fact to prove. This is really, you get this by applying fact one twice. So fact one was about one-outable elements. Because two-outability is really saying one-outability holds twice, I can just apply fact one twice. The only additional thing I need is a pigeonhole principle. So let's see that. Okay, so first, let's apply fact one and observe that there are this many elements, n minus s naught times n minus f elements, which are one-outable for s naught, meaning I could swap something to add something. So we're assuming that all of these lie back in the family, which means that there is some rainbow independent set in the family which contains at least an f fraction of these elements, just because there's f rainbow independent sets, and by the pigeonhole principle, some individual rainbow independent set needs to contain an f fraction of them. Okay, so that is true. And now I'm going to do a similar trick to this deletion thing I did before with one-outability. So yeah, so I obtain S1 primed by deleting from S1 all those elements which were one-outable to S naught. So now I get, since I've deleted some stuff, I get a smaller rainbow independent set, and I can just apply fact one again. So fact one now is going to tell me that there are at least this many elements, which is to say n minus the size of S1 prime times n minus f elements, which are one-outable to S1 primed. Okay. Now this expression here, n minus the size of S1 primed, well, this is certainly at least the number of things I deleted to go from S1 to S1 primed. So this expression is at least this, because that's the number of things I deleted, which means this is true. So I have found the desired number. So this was the number that appeared in the statement of the fact. I have found the desired number of elements x, which are one-outable for S1 primed. And S1 primed was the subset of S1, which is obtained by deleting everything that was one-outable to S naught. Okay. Okay. And what it means to be one-outable, to remind you, is that first I do a swap, I delete something and I add something which is not already in the family, and then I add x. Okay, so I've deleted some stuff, and now by the Matroid property, I get to add some stuff back. So this thing has size one bigger than S1 primed. So I get to add back everything except one element of S1. So I add back stuff, and I get this this rainbow independent set, S1 minus some element x naught minus x primed plus y plus x. Which is to say, x is one-outable to S1 minus x naught. Okay, but of course, x naught was one-outable for S naught. It was chosen in that, like, x naught was one of the things that I deleted to go from S1 to S1 primed, which means it was one-outable for S naught. So we've proved both the conditions for two-outability. So all these elements x, which we found here, all these elements which are one-outable for S1 primed, it turned out that all of them were two-outable for S1. In the sense that it's one-outable to a rainbow independent set of this form in which x naught is one-outable for S naught. Okay. I realized that was a little bit complicated, perhaps, but hopefully it was comprehensible. Yeah, so I'm applying fact one twice, iterating this notion of one-outability to get a better lower bound of the number of two-outable elements. Okay, so now in the same way that you can prove simple corollaries from other lower bounds, here we can prove a corollary, and this one is non-trivial. So this is actually a fact that was proved by Gillen and Webb. This was the first non-trivial lower bound on the number of transversal bases. We can prove it here in a different way. So this is a different proof of the fact that you can always find, of the order of square root n, genuine transversal bases. And the proof is exactly the same. If you had not managed to find this many transversal bases so far, there would be some non-transversal basis. In fact, 2 would tell you there's many ways to extend it, and one of these must not already exist in the family. Okay, so that's good, but we don't have to stop there. We can keep iterating this forever. So I'm going to stop giving detailed proofs of things. But the idea then is to just iterate this this idea and define a notion of I-adable for arbitrary I, which informally it means that I can apply one addability I times. I can do I swaps, move I elements from one rainbow independent set to another. So I get this chain of I swaps, and then at the end I get to add something. And in exactly the same way that I proved this lower bound of the number of two addable elements, I can prove a recursive lower bound of the number of I addable elements. I mean, really, I'm just applying one addability and I addability here to show that the number of I plus one addable elements should be larger than the number of I addable elements by a factor of n minus f over n. So this is not quite true. It really should be this minus something, because there's some issues with things not colliding with each other. But morally speaking, this is the recurrence. And this recurrence is obviously going to blow up if f is less than n over 2. It's going to blow up in the sense that for sufficiently large I, this gets as large as you want. And of course, that is good because that means that if you ever have a collection of f rainbow independent sets where f is less than n over 2, that means you just need to take I large enough until the number of I-adable elements is going to be just larger than the total volume of everything you have, which will allow you to add something. And that's really how the proof goes. So if you would like to see some of the actual details of how you deal with the minus terms, and there's some other annoying things that are actually not very easy to resolve annoying things, but I mean, conceptually, this is how it works. Yeah, so that is all I had prepared. So yeah, that's all.
Thanks very much, Matthew. Are there any questions? Okay, I'll start with, oh, go on, Jim.
I have a question. So that in this paper with Kerry Webb, we looked at two things. So one was the number of disjoint transversal bases. And then the other thing was if you have fewer bases than n, so we showed if you have around square root of n bases, then you could partition it into independent transversals. Did you think about that variation at all?
You can partition it into independent. So what's the setting? So what's the difference?
Instead of giving you n bases, I only give you square root of n bases. And then I can partition that into independent transversals. So I don't give you all n bases, I give you fewer. Can you partition it fully?
We did not think about that. So actually there's a even more general conjecture by Kwan, in which
I think this fits into the more general framework though.
But so our methods do work for this Kwan's conjecture is you've got like an n by n grid of bases, and you want to choose a representative from each cell in this grid such that each row and column is a basis. And our methods do work to prove something very similar to that in that setting, which I think is more general than what you're saying. So maybe it does work.
What do you get that you get a certain number? I don't think it's the same because you have to really partition it up, right? I mean, I'm giving you square root of n, and I need to fully partition up the n times square root of n elements into n sets of size square root of n.
Yeah. So this is not something I've thought about, so I'm not sure, but it does sound like a special case of this Kwan thing, which I can't. Sorry,
I think it's true that if you had the Kwan thing, you would have this result. I mean, this thing that I'm talking about is a special case of, I mean, is weaker than Rota's basis conjecture because I'm not giving you n bases, I'm giving you fewer. And the Kwan thing is yet more general, but the weakening that you get, I don't think says anything in this case. I thought about it a little bit.
The weakening of Kwan's thing doesn't say anything.
Yes, I don't think.
Okay. If you thought about that, then yes.
So as far as I know, the So I mean, when we did the n over log n, I tried to get n over log n for this problem as well, because we had roughly square root of n for both of the other versions. So I tried to get n over log n for both, and I couldn't do that.
That is interesting. Yeah, I haven't thought about that at all. I wasn't aware of the existence of this this interesting variation, but I will. Yeah, one that I do know about is Aharoni and Berger had a different sort of weakening of a different direction to weaken Rota's basic conjecture, where you try and cover with transversals instead of packed transversals.
Yeah, that's relatively straightforward. So I mean, it follows from their general method, but getting 2n is kind of easy with
Right.
greedy methods.
But it would be nice to get less than 2n to sort of push that as far as you can down as well. So that I've thought a little bit about, and it's not clear how I can do better than 2n, but I had not thought about the other thing that you said. Thanks for the question.
Yeah, my question, it really was ironic that Jim and collaborators did probabilistic stuff and you guys did Matroid stuff. Do you know what probabilistic techniques might add to your arguments? I mean,
so yeah, I had really hoped that I could do something. Somehow the reason for the log is like some coupon collector type reason, and so you sort of hope that maybe there's some local lemma stuff, or maybe there's some sort of random greedy, like instead of making the random choices all at once, you like make the random choices one by one in such like a nibble type, like a Rota nibble type thing, where you're sort of running a sort of more guided random process. I was not able to make anything like that work. There are certain obstructions which I think there's the potential to, so somehow if you want to prove the entire thing, I imagine maybe what you would do is you would try to sort of prove an almost theorem and then complete it with absorbers or something. Like you would have some way to, you would have some sort of structure which lets you complete the almost problem to the full problem. And it seems like for something like that, you would want the kind of flexibility that randomness gives you, maybe. Yeah, I wish I had more to say on that subject, but I don't know.
We all wish we did.
Are there any more questions? Okay, well, thanks again, Matthew. I will stop the recording now.